Okay, so let's start with the talk. First of all, for those of you who don't know me, which will be most of you, I guess, my name is Arnau. I'm from Barcelona. I'm a student of maths and computer science at the University of Barcelona. I'm also the president of a non-profit hacking organization in Barcelona. I founded with some friends at the faculty. And I'm also a collaborator in the organization of the R2Con, which is the Congress about Radare2, which is held every year in Barcelona. And probably most important, then who I am is who am I not. I am not a professional reverse engineer, and I am not an expert in Radare2, and I am not a developer in Radare2, at least a core one. This is important because that goes straight to the motivation of the talk. That is, at the very beginning, just demystify Radare2. There is a lot of myths around it and being very difficult to learn and do stuff. So we'll try to demystify it. Then, of course, following the previous one, I'm really interested in trying to give you simple explanations that came from a non-advanced user, which I guess will be helpful for many of you. Also, it is a great way to organize and share the knowledge about Radare2 to make just a concise 2-hour pack lab. And also, I strongly believe that conferences of all kinds of conferences should have introductory talks to some topic, in this case, Radare2 and basic reversing with it. And that's my motivation for having presented this paper, this talk, and for being here today. First of all, quick poll, who are you? How many of you are students, undergrads? Is there any undergrad? Okay, that's cool. I'm also undergrad, so we are two right now. Maybe masters, PhDs. Okay, how many of you are working in InfoSec? I guess most of you. How many of you are doing low-level stuff or reverse engineering as your main work? Okay, and those of you, mostly the ones that do low-level stuff, reverse engineering, I guess you will know Radare2, but how many of you use it, like, regularly? Okay, that's cool. That's really cool because I tend to say that if you are people that use Radare2 and are working in reverse engineering as professional field, I have very little things to teach you, because this will be an introduction to Radare2 and some basic reversing for people not introduced to that. But as I have seen, most of you, the vast majority, don't use it or don't work on reverse engineering. So I think it will be pretty interesting to see how it goes from an introduction standpoint. And this will be the outline of the conference. And before I go straight to it, if I will take a minute, the ones that are with computers, if you want to follow the demos, you have those URLs to download some Crackmes and one of the other demos I will be doing. I will let you 1 minute to copy it. And there you will have it. For the first link, you will download the whole pack of Yoli Crackmes, which are Crackmes made by POF. It's a computer researcher based in Barcelona currently. And it's funny because he did those Crackmes to teach his wife to learn reverse engineering a long time ago. And they are still pretty useful and very basic for people getting introduced to reverse engineering, and I still love them and use them every time I can. The other one is just the pack of complete samples from accompanying a book on reversing. It is Secrets of Reversing by Alan. I guess it's his name. And this is a pretty cool book on reversing. Great introduction, in my opinion. And we will be using one of his samples to do a couple of demos. So I guess most of you will have it. Yeah. So I think, okay. If not, it's really easy to find them. Just look for Yoli Crackmis or secrets of reversing ALAM samples, and you will find at the first search. Okay, let's go straight with it. First of all, I'm gonna cover basic overview of Radare2, and I think this will be useful because most of you didn't answer when I asked how many of you used it. So let's go to it. First of all, in case you know, Radare2 is a free and open source reverse engineering framework that is rewritten in C by Pancake. His name is Sergio Alvarez. He's a mobile security researcher currently, based in Barcelona as well. And it says rewritten because initially it was Radar, not Radare2. It was born as a forensics tool to care for data, mount partitions for his work, like more than 10 years ago. And then it evolved as he needed to add some stuff or CTFs or his own needs. And then there was a moment that it was a completely mess, whole monolithic project without any real structure. So he decided to rewrite it entirely as libraries, and so we will see the structure a little bit later. But that's why there is a 2, because there was an initial one. Radare2 is a framework that is built from scratch without third-party dependencies. That's kind of interesting because you have the libraries, for example, the analysis libraries, the binary information libraries, and you can get them and include it and use it on your projects without having to build upon the whole Radare2 framework. You just can grab the library you need and use it as it. And it doesn't really have any third-party dependency. For example, I remember that at the very beginning, I guess it was little dependency on end courses, and Pancake just rewrote some kind of pseudo end courses for his needs, and that's it. And of course, it's really portable, scriptable, and extensible through plugins. We will see a lot of that afterwards. More formally, and the formal stuff, it has a release timing of 6 weeks. It's based on the Rust release, and it's not really fair that I say that, but it has a really great community. And there is the Congress held annually in Barcelona, early September. So I will invite you to come to visit it. It's a really cool Congress. Let's go to the capabilities. What can Radare2 do? First of all, of course, it's a reverse engineering framework, so it can disassemble binaries of several architectures, operating systems. It can analyze code and data, data structure, references to functions, all that common stuff that you would expect from a reverse engineering framework. It can also be used to do low-level debugging, and it has some really cool stuff to do exploiting. We will cover a little bit of this afterwards, not that much, but just a brief on how can we go to exploiting part with Radare2. And of course, we can do binary manipulation, patching, and all kind of stuff. Then we have, as well as I said previously, it was born as a forensics tool. So of course, it keeps its forensics capabilities. Mounting file systems, partitions, data carving, and that stuff. The point is that it's probably not the main focus right now of developers, the forensics part of Radare2, but still you have it, and it's built in Radare2, so you can use it without having to change other tools if you are doing some kind of reversing involving malware analysis with, and you need to mount some file system or whatever. You can do it just with it. It has also cool methods to extract metrics from different binaries, and it's quite useful for classification. It has entropy modules. It can, for example, there is a cool option that lets you make block-based hashing. That is, I can define, I want to compare different binaries. Okay, you make a hash of those binaries and you know that they are different because the hashes don't coincide, but you don't know where it is. And if it's a huge binary, then it can be a problem. So it has integrated, for example, okay, I want to make hashes of every 100-byte blocks. So it compares block by block, and you can see where it is changing exactly. And then you have, you can do as well kernel analysis and debugging. I won't go into kernel analysis today because, first of all, because it won't be enough time to cover it, and second, because I'm not really into kernel analysis. So I can point you to where to go if you're interested in doing more kernel stuff, but it won't be really extensively covered here. And what has Radare2 support? What supports it? So basically all of that. I don't expect you to read it, but briefly, it runs everywhere and supports everything. You can, any operating system that you have, it can run, and it supports almost any file format and almost any architecture out there, probably more than those that are written here. And usually when it comes out some new architecture, some new file format, it takes very little time to be supported. And if it happens that you have some really weird file format or architecture, or you would like to have it supported and it is not by default, first of all, ask on a Telegram channel or REC, because it's probably supported, but no one updated the document. And second, if not, just open an issue, or even better, make a pull request. But usually almost everything you might encounter is supported. Let's go straight to it. In case you don't have it, the best way to get Radare2 is through the Git repository. Just clone it, go into the directory created, and use the sysinstall sh script. This script is really nice because it will build everything for you. You don't have to mess with make files or anything. It will install it system-wide by default. If you are interested in installing only per user, then you can run, instead of install sh, there is another bash script called user sh. In that case, it won't ask you for admin permissions, but this is the common way. If you're on a Windows machine or a Mac or any other fancy platform, you can check the website for binaries. There are the precompiled binaries for most platforms, and also there are the instructions to, if you want to compile it on your own for any of your machines. Okay. And yeah, this, please. And it's kind of a meme, but it makes a lot of sense. There's a huge problem with Linux distributions in particular Debian. They are using a fucking old version of Radare in the repositories, and many times there is people complaining that this feature doesn't work, this is not supported, and it's just they are using a build from 3 years ago or 4 years ago. So please, if you will be happy and everyone will be happy using Radare2 from Git. If not, if you don't want to be updating everything, I just forgot to mention that the last command, install sh, you can run it every time you want to update Radare2, and it will automatically pull the repository and install it. So you don't even have to bother of pulling repositories. Just every time you want to update it, run this command, it will pull it and install it. And there are the releases every 6 weeks, as said. So in case you don't want to be just updating every day Radare2, you can stick to the releases. But the preferred and recommended way of using it is from Git. Okay. And what are the tools included in Radare2? As I said, it's a reverse engineering framework, and it has many tools included, not only the main Radare2 as it is. I have listed here the tools. There are bunch of them. The first one is Radare2, which is a base converter. It's a very basic base converter to make some operations, binary to hex to decimal. It's scriptable, really useful. Radare2 is the standalone binary for extracting binary information, which is also integrated into the Radare2 shell as well. Radare2, which is the assembler and disassembler. You can specify your architecture, the bits of the architecture, the endianness, etc., and you can assemble and disassemble with it. Then there is the Radare2, which is the crypto hashing utility. It has implemented the most known crypto hashing algorithms. You can check out them. Also Radare2, which is the included binary diffing tooling. Radare2, which is here, it says it's to compile tiny binaries, which is true, but it's the official description, but I would say it's more like an exploit helper, in my opinion, because you can basically craft your own C code that you want to be done. You want to inject as shellcode, basically, and it will create the shellcode for it to execute. It will drop all unnecessary stuff and give you directly the shellcode. Of course, as it was growing as an exploitation assistant, let's say it that way, it has some other typical things to do that I will show later, like doing the bridging patterns and searching for the offsets and that kind of stuff when we are looking for the memory position to inject the code. Then we have Radare2, which is running, it lets us to run Radare2 with different environments. What does this mean? It means, for example, that we want to spawn a shell of Radare2. We want to work on a file. We are reversing a file, but we want to make it like if we open from that working directory with that environment variables with these arguments, so we can just craft a very little file with that. And with Radare2, we will pass the binary and with the environment as well. And it will be loaded as if it was actually running from the environment defined. It's quite useful for some of the tasks. Then, of course, there is the R2PM, which is the package manager. Radare2 is really extensible via plugins. There are some of them, the most used, that are actually included in the core Radare2. When you just install it, you will have them. But there are other ones that can be installed through the package manager. It's really, really easy to use. R2PM, install, and the name of the package, and that's it. And you can obviously uninstall and manage it. It's a very simple package manager, but really useful to get track of all your external plugins. And then for sure we have Radare2, which is the main tool, which is the actual shell for doing all the stuff, and it includes the functionalities of most of the other tools. I mean, we have standalone tools that are using some of the libraries we said before, and as well we have Radare2 that is including all those libraries and using them inside the shell. So you can use them as standalone programs or inside the shell. It depends on your needs. So let's go for comments or interaction, and let's go straight to it. I hope you have your Radare shell just waiting for the opening. So how to spawn a Radare2 shell? First of all, R2 is a symboling for Radare2. You will usually see R2 when calling Radare2, just a formalism, but just in case. To open a file, just R2 and the path of the file. Then this won't open in write mode, which means that we won't be permitted to write in the file. To do this, we will have to open it with the write flag, which is the W. And if we want to debug, so it can run the process and attach to it, we'll discuss a little bit about how debugging works afterwards. So in one debugging session, we have to use the -d flag when opening. Then there is another interesting flag for me, which is, okay, I don't want to load any user settings, any custom settings. That is because we can custom and craft mostly everything from Radare2, its options, configurations, or a lot of stuff. We will dig into it in a couple points afterwards. But just in case we want to just open a shell without any custom settings loaded, just with -N, we will do it. And then there are two other interesting and quite useful sometimes commands that is, okay, I just want to open a Radare2 shell, but I don't really want to open any file. I just want to look through it, or maybe explore the configuration to configure it, or whatever. I just don't need to open a file. You have two options. First one is just with a dash. We'll just open with this macro, which is it will give us half 512 bytes of memory, so we can write in it, and we can modify it. We can write whatever we want, and we can also save it to a file. And there is, okay, I don't really want anything to be opened or memory to be allocated. I just want to look through the shell and their options. So with two dashes, it will spawn a shell, but it won't attach to any file. So this is one of the important slides here. R2 commands are said to be difficult usually because are not common. Their syntax is not the most common, lastly, but it's not that difficult. It's based on mnemonics. Mnemonics means R2 commands are really short commands, usually short, where each letter means one thing, and the letters the leftmost letters are the commands. Then we have the following sub-commands. So, for example, if we want to seek to an offset, we will use the S. If we want to print the hexdam, we will use px to print hexdam, print the disassembler, pd. If we want to write hex pairs, write assembly, analyze all, info all, or quit. And everything works like that. So sometimes you can even guess what will be the command. And for example, I will make it is here. I don't know if you see it. Yeah. So, as I said, let's say that I want PD 20 lines of disassembly. Print disassembly 20 lines. And you don't see anything because it's freaking okay. Great. So now we want to seek to, for example, I don't know, this position. So we just seek to this position. Oops. Yeah. Okay. And the pointer changed. Okay. That error is just because my clipboard doesn't work well, and when it passes tab, it just done that. Okay. And if we want to, for example, if we wanted to write something, here we can do it because we have not opened it in write mode. So I will open now something that I can write, but not binls, of course. And if we open with the write flag, now, for example, print the hexadecimal, we see the hexadecimal representation at the offset we are located. We don't need to print the default values. The default amount of hexadecimal, for example, we can specify the number of bytes. The default values are also configurable. So if you, by default, just want to print the hexadecimal of 3 lines, you can just configure it that way. And now, we will, for example, I want to write hex pairs, as we said, 9090. And here you can see 9090. So that's it. As it's just that. This is quite important. But probably even more important slide is this one. Now you have everything you need. Radare2 is really cool because it has inline help, which means that for every command and every subcommand, you can get inline help while in the shell for all the options and everything. And I will show you just right now. If we just open our shell, we just throw a question mark, we'll have all the options, all the commands available and their description. For example, let's say we want to go to the analysis command, which is the A. So we go to A and we append a question mark. We will see its subcommands. We want to deal with analyzing functions. Okay, so we can analyze functions and a question mark, and we will see all the options for function analysis. We want to list the functions. We go here and list the functions. And there is only the entry point Y because we haven't analyzed it yet. So we just analyzed the code, and now analyzed functions list. We will see all the functions it found. This is ls, okay? So keep in mind, just appending a question mark, it's the best way probably to move on, because you don't really need to know every command, every mnemonic. You will get used to most of them, at least 10 or 15, which are, with those you can make 99% of regular stuff. But if you need to look for something, just append a question mark and you will have all the descriptions and all the options running for it. Okay. Some handy tricks that I found quite useful and are interesting when dealing with Radare2 is, for example, usually when we throw a command, if we append a J at the end or J with that curly brackets, it will gives us the output in JSON format, both or condensed or expanded. I will show you. For example, I is for information. We'll see the options. Okay, let's say I'm interested in the sections of the binary. So information of the sections, here are the sections. Let's say now I want to get it in JSON. Okay, this is JSON. And I want to read it like pretty. So that's it. I will advance just one slide, but I'm coming back in a moment. That's really cool because we can pipe with the shell commands directly, and we can even run shell commands from it, which means basically that we can do this and pipe it, for example, to less directly. We can look for it, can do whatever we need. And I'm not really sure if this works right now. Yeah. We can direct the pipe to a file. And now we can call it directly. So another cool thing is we can append cube on most of commands as well. And it will give us a quiet output. For example, removing some non-important or not essential stuff. This is quite useful. For example, in the sections example, just appending a queue. So it will give us a way briefly output. Sorry. That's it. And it has implemented an internal grep. That's really interesting. And you would say, because I advanced, okay, but why don't you just pipe and use grep? There are a couple of reasons. First one is not every system have grep. If you're running on a Windows, you don't really have grep installed, or some versions of BusyBox that don't have grep, and you can have Radar installed and wanting to work with that. So you have internal grep that you can use it right there. So for example, if we list the sections, we can grep for sections that contain the word data, and that's it. Then we can run native shell commands from the native shell of the system with the exclamation mark prefix. That's quite interesting, that it will return to the Radare2 shell without losing the session. And finally, one interesting thing is that we don't really, there are some modifiers. I won't go deep with them, but one of the most important or most used is the temporary seek, is with the @ symbol, and it basically means that perform the operation you are telling at an offset, but without having to be seeked to it. that you will understand with an example way better. For example, if I want to print this disassemble of 16 bytes at, I don't know, here, oops, at this memory, I would have to seek there, as I told you before, and now print the disassembly of 32 lines. But if I am just here, use the entry point where we arrive just spawning the shell, I can do this without having to be seeked to the other place, just with the temporary seek. And it was like, you will see that it's the same output, but we are still seeked where we want. This is quite useful because most of the times we are dealing with main function and we are working with it, but we want to explore another function, but we don't really want to be seeking from back and forth to one function. I'll just do a temporary seek, and that's solved. And yeah, let's go straight to it. Let's make a very simple first demo of the crack me. I guess it will be the number 2 of the Yoli ones that I put before. Just to show you, do you see it well, the screen? Yeah. It's just very simple. Crack me, you put a password and it says invalid. Our goal in this crack me will be to make the program accept any password. Okay? Then afterwards we will see when we talk about emulation why I'm doing this now, and afterwards I will be doing like extracting the actual password. Actually, the challenges, if you have downloaded and looked to the README, says that you have to patch the binaries to accept any password. So we are being legal. Okay. Do you have the crackmes downloaded? Go with the okay. We'll follow it. First of all, if we want to patch the binary, how do we have to open the file so we can patch it? That is modifying. Anyone? Exactly. We need the W flag because otherwise we can explore it, but we cannot modify it on disk. Then I will show you a cool trick about modifying the binary on the session, but not on the disk. But now we'll be using that. I will make just a copy. CM2. And we are opening it with the W flag. First of all, what do we want to do? Analyzing it. There is a meme in the community that says that just throw A's to Radare2 and analyze everything, because as more A's you throw, deeper is the analysis. So usually with 3 A's you have enough. There is some experimental analysis methods that run with 4 A's. And some time ago you just opened a session and just did that. And it worked because starting at 4 A's, you can put more, but it will do the same. But then there are other developers that are really funny, and I guess it's starting at 7 A's. This is this message. And doing anything. So you can throw a bunch of A's, but no more than 7 or it won't do anything. Okay, so I guess we will have it properly analyzed by now. So we can, for example, list the functions, analyzes functions list, AFL, to list the functions. We're interested in the main one, And now, what can we do as we know? We could seek to the main function, which is this is a flag, so we don't really need to copy the offset. We could just seek to main. This is a flag. We could as well print the disassembly at main, which is printing the disassembly at the offset referenced by the main flag, but without seeking to it. And there is another option which is PDF, which basically is print the disassembly of a function. This is quite interesting because if you specify that what you're disassembling is a function, it will, as it has been analyzed, it will give the disassembly of the whole function with the boundaries. Otherwise, you will have to print the disassembly 20 lines or 10 or maybe 30. So as it has detected the length of the function, it's quite interesting. And we can just seek to main because we'll be using it. You see the pointer change. And then we just run PDF. If we wanted to print the assembly of another function without seeking to it, just the same, temporary seek, PDF, add function, whatever, okay? But in this case, we're in the main, so we can just print the disassembly of the function. How many of you understand assembly? Okay, most of you, that's fine. But that's really fine that some of you don't really understand it, because you don't need it. You don't actually need to understand assembly. I'm not an expert on assembly at all. I can read it more or less, some architecture, but that's it. And you will you will see because you don't really need to understand it, because it's really easy in this case. This is a really easy crack me. So we have the main function, we have some stuff, don't worry about it. Then we have here, oh, there is, you will do it a little bit. Can you read it? That's okay, because then here it's less messy than having all the that zoom. So here we have a reference to a string, which we have here in the comment, and then a call to something that is printf. You don't need to know assembly to know that what's happening here. Okay. Here there is another reference to another string which contains password, colon, space, and another call to printf. Again, you don't need to know assembly to know what's going on here. Then we have something, and then a call to scanf. It was asking us for a password. So again, you don't really need to know what's going on to understand what's happening here. And then here we have an interesting part, which is basically moving some values on memory, making some operations, adding multiplication and so on, and then comparing to values. That's it. You don't really need to get to the exact, you don't really need. If you are starting reverse engineering, it's quite recommended that you go through that with pencil and paper, and okay, this goes to this memory, and then this one is multiplied by this value here. It's really, really useful. But to do most of the things, you don't really need to understand line by line of the assembly. Just go straight to the point. So here we have two printfs of the strings we have seen. Then a call to scanf, some kind of operations with some values that are being loaded, and then a comparison between the value that is stored here and the value that is stored here. And we can see that the one stored, the var ch, which is at the base pointer minus c in the stack frame, is the one that is being referenced here. Okay? We'll see afterwards when we talk about emulation why this is important, or at least why we are interested in it. But now, what we want to do is patch it to accept any password. So here it is a comparison, and then we have a conditional jump if not equal. Here you have the arrows. If it's not equal, it will jump here, which is invalid password. Oh, a reference to invalid password and printf. It's clear, crystal clear. And otherwise, it will continue and it will say, okay, the password is okay, and we are done. So anyone has an idea how to patch it so it always says yes that the password is okay? Yeah? Exactly. Just get rid of this jump. If it does the comparison, but it doesn't care about the result, because if we remove this, it will just go straight to loading the password string and calling the printf. How can we do that? So we can seek if my clipboard is working. Okay. This is the line, print the disassembly of one line. And we will write hex pairs 9090. In case you don't know it, 90 is the hexadecimal of the opcode representation, which is NOP, which is no operation, okay, in x86. So we will write 2 NOPs here. And now we can see, for example, the hexadecimal of just this line. We see that this has been written. And if we, again, print this assembly, we have an op here, we have NOPs, and that's it. That's pretty much it. Now, we can disassemble the main again, and you see that here, just before the loading the password, okay, we have NOPs. And we just quit. Oops, it's not this one. It's the copy. Password, okay, wherever. So that's it. We will come back to this example afterwards to see another demo on another different approach, but that's basically it. And again, let's say I don't really remember how to write hexadecimal values. So I know that write is W. So W question mark. Right, okay, here we have write hexadecimal. Okay, so write hexadecimal. Do we have any more options? Yes, we have more options. So we write hex pairs and seek at the end. For example, we can write hex pairs and then seek to it. Or, I mean, this is the, when you have done this a couple of times, you usually remember it. But if not, just append a question mark and look for it. It's really, really quick to do. Okay, that's it. Now we will dig a little bit on the visual modes and navigation. Yeah? No, not necessarily, of course. Yeah, really good question. In this case, it was really easy because NOP is, everyone knows that is 9090. But no, you can just assemble the instruction as it is. You have 2 ways. One is just assemble it, which is using the assembler and disassembler library inside. You can do it both with the standalone utility, which is Radare2, or with inside Radare2, you have another option, which is the write assembly and subcommands, and you can directly write the instruction. And other ways, there is some some visual mode that you can just, for example, usually if you want to change one jump from not equal to equal or something like that, you can just use the cursor mode that maybe I will use it a little bit at the end on the last demo, that you can basically place to a specific byte and just decrement. And usually when, for example, when you're on a jump instruction, just incrementing, decrementing a byte of the hexadecimal, you just are changing the jump values. But yeah, of course, no, you don't really need to know all the hex values. But if you would, you can make it with the assembler and disassembler. Yeah. So the visual modes, okay, all the shell is cool, but we want more interaction. We have more interaction. We have the basic visual mode, which is just with the v command. We can run into it. I will open a file. Otherwise, it would be just nothing. For example, with the v, we have here the hexadecimal representation. Here we can use the scroll. I'm scrolling right now. We can just move right like this. And with P, we can rotate the print mode. That is, here we have in hex representation. Here we are in disassembly. Here we are in disassembly. And if we were debugging or emulating, we would be seeing the register values and so. Then this is another representation on, because it's entropy. And more representations of strings, and come back. This is basic visual mode. I won't really waste more time into it because, I mean, it's interesting, but it's not the point to seeing all the options of the visual mode. But 2 interesting things that you can just throw a question mark and you have the help, the visual mode help. So you can have all the things that you can do inside the visual mode. You have here explain. So you can just navigate through it. And another thing is that if you want to run an R2 command while in visual mode, you have to just prepend a colon. It's like V you are used to using V. I am not, but I am used to use Radar, so it's more or less the same. You can just run a command. For example, if you want to analyze the functions, you're here, want to analyze the functions, okay. And I'm going to do disassembly, for example, and now I want to list the functions. So just colon and then the command, and you will see it. And then with a return, you come back to the visual mode. Then there is the graph view, which is really cool for all reverse engineers and really useful for following the flows of the function, what's going on in there, what are the branches, switches, if-else clauses, loops. It's a really visual way to do this. For it to work, to show something, you have to be seeked to a function or apply it to an offset function with the temporary seek we have seen. And you can move it with the old style A, G, key, L, or also with arrows, and you can zoom in and zoom out with plus and minus. It has more options, of course, but those are the basic ones for navigation. And again, you can just append a question mark and see what are all the options. So let's see how it looks like. For example, let's seek at main. And here we are. This is a really poor graph because it's so simple. So I will open, for example, binls, well, temp ls. We analyze it, seek at main, see the graph function. Okay. You can follow it. For example, you have all these OG, ODE, OAB, they're here. You can just follow the paths with those shortcuts. You can make it just smaller or bigger, whatever you need. You can also rotate modes here, which is kind of cool. And of course, you have with the question mark, I just tick the question mark, you have all the options with graph views. So you can play with it. And then there is another one which I'm in love with, which is visual panels. And they are extremely useful when doing some kind of debugging or some parallel things. And they're basically a paneled terminal, a pseudo panel terminal with different views. You have the disassembly here, the stack here, the registers there. Usually the default panels that it throws are the good ones, let's say that way. Those are if you are debugging, it will show one panel. If you're doing other stuff, it will show another one slightly different. But you can, of course, customize the view panels and add your own and move them around, whatever you like. It looks something like this. Let's see. Yep. Have the disassembly. Now you see it good because I have a lot of zoom for you to view, but on a regular computer or a decent bigger screen. So you have here, you can with tab, you can just move it. This is a really the compilation, this is like a toy, the compiler. This is not anything fancy. It's just getting a quick translation. There afterwards we will talk about the compilation and so. And you have, for example, here the functions listed and the symbols. And if you were, for example, debugging, for example, you could have the stack and have some panel for stack telescoping, which is getting the references and the values, and other for the registers. That's quite useful. Okay. So again, you can just it's with V exclamation mark and just append a question mark and you're good to go. Let's go straight to the configuration and customization of Radare2. That's it. Basically, use the E comment and its subcommands to tune Radare2. The E stands for the evaluable configuration variables. There are a ton of different evaluable variables, configuration variables that can be tuned to your needs or your preferences to use it within Radare2. If we just throw an A, it will show all the configuration variables, and you will say, "Holy shit, what the fuck?" Yeah, but there are better ways to look for it and see what's going on. If we append to question marks, we will see the descriptions of them, But of course, first thing you would know, okay, we can grep because we have internal grep. For example, let's look for something that has to do with bytes. So we have the options that have to do with bytes and their descriptions. And these are one of the ways of looking for that. There are more, and I will show you my preferred one. Yeah, look for them with internal grep. We can list the possible variables we just make e the configuration variable equals a question mark. If it has a predefined set of values that it can take, it will gives us those. I guess, for example, EASM architecture, it gives us which architecture can be defined here as a variable. That's an example. And a lot of them are just binary values, true or false. And we can set a new value, just send a assignation. What is, I guess it have it here. Yeah, but I will go now. I will advance it. The best way for me to explore all the configuration is with the visual mode, because if we just throw VE, or if we are in visual mode and press E, we can explore all the configuration variables structured. So for example, we're interested in the, I don't know, graph. So we just throw an arrow, and we can see all the values and their descriptions, and we can navigate through it. And we can even change them. For example, graph line mode. We can define a new value. And if it's another, for example, a Boolean value, we can change it directly. That's it. This is a nice way to explore the configuration variables, but I said, don't be overwhelmed with that. Usually, the configuration variables that you would need for a particular binary are loaded by default, because the binary formats, the architecture are auto-detected and automatically put in the configuration variables. It's more like, okay, I want the block size for my disassembly printing to be of, I don't know, 32 bytes instead of 256. So that kind of stuff. But most of the hardcore configuration variables will be detected by default, and you won't have any problem. Are still there in case you want to force it, because, I don't know, polymorph malware or whatever, you want to explore it with viewing with different architecture or something, so you can have it. But you won't be messing with configuration variables most of the time, just very little. And what's cool, another cool thing that I don't have it mentioned, but I guess it's important to mention, at least funny. With AC, it's the colors. It's all the configuration or color mapping. We have predefined themes. In my case, I have selected the dark, but I don't know, whatever. And you can just have another color map. And if you press ECR, it will give you a fancy random color map. So, what is more interesting is that in visual mode, you don't have to do it every time. You just capital R and that's it. And here, if you want to have some configuration variables loaded by default on each session, for example, the color mapping, or I will show you mine in a moment. You just create a Radare2 file, hidden file in the home folder, and it will be loaded by default. I can show you mine. Where? This is just e-commands for configuration variables that will be loaded by default. I'm going to discuss them a little bit. The first one is just setting the color scheme, and the other ones I will talk here. Those are probably the useful configuration variables for almost everyone. First one is CCRR-UTF, put to true. That's good because most of computers that we will be using nowadays support UTF characters in the terminals, and you will see the difference. You will see why it is important. If I just run it this way, remember the -N flag is to don't load any custom settings, so it will ignore my custom settings file. Okay, the color map is, well, it's kind of old school, but okay. But look at the arrows, please. Or with graph views, Look at the boxes and the arrows. So just go, and you're good to go. That's way cooler. And it's even cooler if you enable the curvy corners. It's just a tiny thing, but it looks way better. Those corners that are really, really straight, you can make them curvy. Here we go. So those are really, non-functionality related configuration, but that are cool to have, and your eyes will thank you. Then there are one more I will show you. Okay, I will go to the ASM use case that is right there, which is basically showing this assembly in uppercase. If you are more like old school stuff and you want to show the disassembly in uppercase, it's as easy as that. And then the show opcode description and enable pseudo syntax. That's really, really, really cool, especially for people getting introduced to reverse engineering, or even for reverse engineers that with experience, but that they are faced with a new architecture or a new system. They don't really know how it works. The first one is it will just append a comment after each instruction saying what is this doing. It's just a description. We can see this. For example, this is I will have to put it a little bit smaller. I won't expect you to read what it says, just to see what it happens. Here's describe. I just throw the EASM describe equals true. And now you see all the red things. I think I can make it a little bit. It's just describing what's happening. Okay? Like, it's very, very basic, but if you are in an instruction set you don't know, it's a cool way to learn some new assembly instead of getting to the manuals. So, of course, you have to go to the manuals for in-depth, but for a quick look and just understanding what's going on, it's quite useful. And even if you don't really like that assembly assembly way of doing things, you can do another thing. Let me deactivate that, which is ASM pseudo, which will make a pseudo syntax more human friendly or high level friendly. And basically it will show that instead of assembly. Look at this. With ifs and variables equals to ax minus 3 and that kind of, it's not the compilation at all. It's just making a one-to-one translation between the assembly and some other syntax like that people coming from high languages will appreciate if they are getting introduced to that. Okay. And then there is that other trick that I mentioned you before, which is the one of the IO cache. This lets us to write into the binary that is loaded into the memory, but without modifying the actual file that is on the hard disk. That's quite useful in case we want to play with some binary, with some crackname, with whatever. We want to see, okay, I want to change that, see what's happening, but you don't want to store that or modify the binary of you just have been a 2-hour session reversing something and you missed, oh fuck, I don't have I'm not on a copy of the file. I just don't want to do this again. So you can enable IO cache, and it's basically, it makes a cache and you can overwrite. It won't say, it will permit it to you. For example, if you try to write something on a file that you have not opened with write mode, it will say you can't write here. Okay. But if you enable the cache, it will act normally. It's just the file and disk won't be modified. Just the file that is loaded into memory. You can work with it, and when you are out of the session, that's it. And we will use it afterwards in a demo on emulation. Okay. We've seen that. Okay. I guess that's it. Okay. Yeah. let's go straight to code emulation. This is one of, I guess, the longest point on the outline. Mainly because two reasons. One is, I don't know why people is not using emulation, in particular not using emulation in Radar, and it's really useful. And second, I had to give a talk like 10 days ago about emulation with Easel, so I just had to make it anyway. So I stole my own content, so it's not stealing. And we will go through it. And what is emulation? Basically, in case someone doesn't really know what emulation is about, is just simulating the execution of code of a CPU of the same CPU architecture or another CPU architecture. That's the point of emulation, that we can simulate executing code that does not belong to the architecture of our machine. Yes, that's basically what you do when you run games from old or not that old consoles. All that kind of stuff is basically full emulation. You're emulating, you're simulating the execution of code that is not meant to be run in your architecture. But the kind of emulation we are dealing today is not the emulation seen as a part of running games or all software. Is more a way, is an assistant for code analysis and reverse engineering in particular. We're interested in it because it lets us to understand specific snippet of codes of binary from architecture or another architecture, doesn't matter. And it's quite useful as well because, let's say, you are analyzing some kind of weird malware and you don't want to be pwned. So you can do this, you can emulate some parts of the code that is not the whole binary, just I'm interested in that section that it looks like is some routine for encrypting the code, or it's some routine for whatever. So you can just take that snippet of code and see what's going on there. And of course, you are not running it because, yeah, everyone uses virtual machines and all that kind of stuff, but I won't discover you that they are exploits for escaping virtual machines or all that. I mean, of course, use virtual machines, use sandboxing, but if you're threatening with something really, really delicate, before going to debugging or trying to executing something, unless you have a dedicated machines, then you're good to go. It just fucks up, you just dump everything and install it again. That's fine. But if it's not your case, so emulation is a really good friend for you. Then, of course, it helps on debugging and on code analysis. You would see when we are doing analysis with 4As, and I guess with 3 as well, in the Radare2, it's using some emulation for branch prediction on functions and to reconstruct some of the paths. It's kind of tricky. I don't really understand how it's done, but I mean, I have not coded it, of course, and I'm not into that part development, but it's using some kind of emulation just for analysis to see, okay, what's going on here with that function and which information can we extract from that, just from looking at particular snippets of code. And of course, if we want to explore some non-native executables, we have to do something. I mean, if you want to explore, for example, a PowerPC or an ARM tiny binary, that is not, I'm not saying like very huge applications that you need a full analysis, but just specific things. You can explore it with emulation. You can see what's going on without having to emulate things, debug things, and of course, because you cannot debug an architecture which is not your computer. So one important thing on emulation is the concept of intermediate languages, and just I won't go very deep into theory. It's just an abstract machine that helps in analysis of computer programs. It's just, as the name says, it's an intermediate language between the code and the actual code that is written and the assembly that helps us in the analysis. And it comes mainly from compiling, from the compiling process. GCC is using an intermediate language, and maybe you will know LLVM, which has its LLVM intermediate representation. Mainly, they came out for assisting on compiling process, but are also vital for the compilation. So the IDA, for example, the IDA microcode for the hexarrays decompiler is based on an intermediate language, and we have our own intermediate language in Radare2, which is called ESIL, which stands for Evaluable Strings Intermediate Language, and their characteristics are quite simple. It's a very small set of instructions, and the syntax is based on reverse police notation, which is basically a stack. You will see in a moment an example, which usually means that it is not meant to be read and understood by a human, but more to be executed quick on a machine. Okay. And some of their main properties is that it has infinite memory and set of registers, like many other intermediate languages. It is so cool. It has native register aliases, which means, for example, you are emulating an ARM code, and when you construct the virtual machine that will emulate the stuff you want to emulate, the register aliases will be something like R1, R2, R3. So it constructs the aliases, so kind of put you into the mood of the architecture you are emulating. So it's not like something like, okay, I need to now understand some other names from some other register. They can be arbitrary, but for common architecture, they automatically give you the aliases that you will thank. And of course, as I have said, it is based on a small set of instructions, but if you need custom operations to support for some architecture, even the mainstream ones that have very weird or rarely used instructions, you can just define them. You can quite easily implement a custom operation based on the symbol operations that has ESIL and link it as okay, now this operation will be described as this set of instructions on ESIL. And you can use that. And why ESIL? First of all, we needed the emulation on R2 land, is basically the R2 environment. And it's really easy to generate, to parse and modify, because as I said, it's mostly the most important thing, generation and parsing, because it's based on reverse police notation, which is basically a stack way of thinking. And also it's quite extensible, rather easy, I would say. I mean, it's not trivial, but once you see the instructions that you have at what you want to accomplish, it's not really difficult to add your custom operations or build on top of it. And of course, why not? One of the problems that have some of the intermediate languages is that they are built with a compiler man, and ESIL is built with a decompilation in mind. So that's a good way to see it. So I would describe ESIL as I would say the parser that's running behind ESIL. I would define it as a stack machine on steroids. And I will go straight to describe to you what is a stack machine. This is theory. This is theoretical computer science, which is super cool. And I know I see your faces that you are really interested in automata stuff and all kinds of stuff. I won't go into it. It's just you need to know that there is a stack and there is a abstract input tape that has some input symbols, the current state, and the stack symbol. And then from that, it transitions to another state. And during that transition, it can manipulate the stack, which means basically pushing and pop, making pushes and pops from the stack. That's the basic idea. Yeah. Sorry? I will show it in a moment. We will have a demo just running it. Yeah, here's just the visual animation of what is the reverse. This is reverse police notation, which is basically first the operators, then the operation, and this is basically how it works in a stack. We put the 3 in the stack, we push the 5 on the stack, we read, okay, this is an operation, then let's just pop the operands and get an 8. Oh, magic. And in Radare2, it's quite easy. We can just Now, for example, I will be just not opening anything, R2 with 2 dashes. Oops, sorry. And then AE is for emulation. All the commands are under AE. I will describe the basic commands afterward, but just for you to know, AE are the operation, it is the subcommands that will contain the emulation with easel part. And let's do the same. It's an 8, okay? Very, very basic. It just parses it and gives the result back. So what's the problem with that? Again, more computer theory. Don't worry about it. I don't even understand all of that. But the main idea, we are in a push-down automata, which is what I described. We have an input tape with some symbols. We transition to state. We have a stack that we can manipulate during that transition. And we have to go more into a Turing machine. What does this mean is that we want, for example, with a stack machine, we cannot access a random position of memory. We are limited to the top of the stack, and there are some things that we cannot do. So how can we do this? And the most obvious answer is the correct one, with asteroids. That's also known as cheating. Cheating basically means, okay, let's add our random access operations, and let's add control flow operations to easel. This is part 1, and part 2 is, okay, let's add register access, and let's add an extra tape with random access that will be a virtual memory. That will be a stack for virtual memory to work with while emulating. So that's it. The asteroids that are added to the pushdown machine gives us random access operation, control flow operations, and also another tape, which is basically a section of the memory that will be used for storing all the data we need when emulating. And this is another important slide. As I said, the easel options are under the AE subcommands, which is the analysis easel. And we have, for example, the AI for init, IM for init to memory. Just to point, if we initialize the memory, automatically we have initialized the stack machine. So usually, if we don't need a memory, don't use the IM. But if we need to use it, we don't really need to put first the initialize and then initialize memory. It's already done. Then the instruction pointer. Okay, we want to move the instruction pointer, and now we have kind of familiar instructions. If you have debugged something, which is basically stepping until an offset, stepping over to skip to don't enter into a function, step skip to step skipping some of the instruction, and we can also show the registers. The step skip, for example, I want to mention the difference between, for example, step over is just we are into a function, we just arrive to a call to a function. Step over will just don't go into that function and emulate all the stuff. Step skip is, for example, we are emulating something and we want to go from the offset 0 to offset 10, and at offset 7 there is some operation that is doing something. For example, it's computing a hash value of whatever, and it's not really useful in what we are trying to decode, and it doesn't interfere with anything we are dealing with, so we can just skip it. Okay, I don't want to waste 3 seconds to emulate that because I won't use it. So that's quite useful, the step skip part. And what are the easel operands? So what can we do with it? And I was thinking of putting here a giant table, but just look for the help. I will show you. You have the operands and their descriptions and some examples, even some examples. So that's it. You don't really need to, unless you are building something upon easel syntax, usually you don't care about it. But it's fun to know and how it works. And if you need to perform some custom operations, you would need to use that. For example, this one, the question mark curly, is an if. It's the control flow if. Just as an example. And then we have, gotos and breaks. And We have also initial internal variables, which are basically the flags, and they're prefixed with the $sign, and they're read-only. I will explain a little bit about the flags and why they are like the internal flags, and why don't we have just some, let's say, register flags like a normal, I would say, normal architecture. The point is that those flags, the internal flags on ESIL, are updated every time and at every operation that ESIL performs. But depending on the architecture we are emulating, not all architectures update all the flags in the same kind of operations. So, for example, what is really common is we have the flags, these flags, the internal flags that are updated at each operation in ESIL, but the operation that it's being emulated into in the architecture we're emulating, by definition, it doesn't do nothing with the flag. So we don't do anything. But if it does, then we just create another register, because we have infinite registers in ESIL, the definition, and we just copy the flag we got from the internal variable to the register flag we define. That's the common way. It's kind of weird, but it's really useful because, as I said, not all architecture update the same flags with the same operations, and the internal bars will be updated at every operation that the ESIL performs, and depending on which operation, in which architecture we are dealing, if they update or don't update the flags, then we can just move the values to the register. So here we will revisit our CrackMe from before, and I will demonstrate why I didn't want to just go by hand, because we are lazy sometimes, and why we have to compute things that can be computed automatically. So let's just compute it automatically, and that means basically emulating. And this will be a very basic demonstration on ESIL. Okay, let's run the CrackMe 2 again, just to see that I'm not lying. And now what we will do is, instead of patching, we will see which is the actual value that it will accept as the valid password. We just open it, analyze it. We print the disassembly of the function that is secret main, and we see exactly the same as before. And here, as I said before, after the scanf, there are two values loaded into memory, and then some operations performed, and then a comparison based on the result of those operations. So what we will do, basically, I will start the virtual machine of ESIL here in this offset. I will say, okay, now let's say I'm gonna emulate, I'm telling you what I'm gonna do. I'm gonna emulate this snippet of code, which means I will simulate that I have a program that the only thing that does is just this part, which is the computation that we are actually interested in. So I will seek here. Let's seek here. I don't know if you see it here. Do you see it well, right in the bottom? Yeah, okay. Initialize machine, do you remember A was for emulation commands, and then IM, you have the initialization of the machine. Okay, we can see the registers. Let's do a better thing. We'll do it again. I want to show you something. Okay, so now let's see the registers. Okay, the instruction pointer points to the other we are seeing right now. That's not important at all. But when we start the machine, then the registers, see the stack pointer and the base pointer? They changed. They created a stack of memory for us at those offsets. So now we have a stack that can use as a virtual memory for the ESIL emulation needs. And now here we are. Let's go here. which is the, I guess I will print it, the main function again. We have seek here, which is the beginning of the operations, and we want to emulate until here. So before emulating, remember that I told you that I'm not opening it in write mode, so I cannot write, but I'm interested in seeing what's going on. So now, as it will be writing into that piece of memory that I reserved with the virtual machine, I need write permission on it. So I just enable the IO cache. Okay, and now it will be able to write it. So if I remember correctly, now this is just step until, and it will just step until that address. It will take a couple seconds. If I have not. I wasn't seeking the right place, sorry. Yeah, I forgot to put the instruction pointer to the offset I was. So of course it was running just before, and it was trying to emulate all these printfs and scanfs. So let's see. Okay. This is. Oh, yes. I know, but it's not working. Sorry, wait a second. See the registers right there, stack pointer, and the other ones. Yeah, it was fine. Okay, yes, it was right. Now, what we're interested in looking for is what is the value that it is being compared. So what is the result of the computation that happened here? So this value is on var ch, which is exactly at EBP, the base pointer minus c. So we will just print it. PF to print formatted data, which format would be as decimal, where to EBP minus c. And we have this value. So now we just run the correct me, password okay, and any other password fail. That's it. Oops. Okay, time's passing by. Yeah, okay, we'll go for another more interesting demo, which is the obfuscating encrypted code using ASIL. That's a little bit more interesting than just a random crack me. And in this case, I will be using this one. In case you have it, the defender.exe from chapter 11 from this download. Let's see. First of all, let's print the information. This is an XC, which is a 32-bit Windows executable portable executable file, which means there is no way. Oh wait, we cannot just natively debug it here, okay? But we are trying to do some stuff with it as well with emulation. So first of all, let's analyze it. Let's list the functions. And now I will skip one boring part that is looking for its function, what it is doing, but I can tell you that this function has something interesting. And we seek to it, print this assembly, and okay, it's doing something, some stuff. We don't care, okay? We don't care what's going on here. But if you see it here, it's doing moving some memory on some registers, then XORing some stuff, again XORing some stuff, again XORing some stuff, then same, jumping back, jumping forward, and then we have, let's print the whole function, this little push, pop, jump triad that, in case you're not familiar, they're usually, it's a quick trick to perform code obfuscation. So basically, this will be a very simple cipher to work with. So that means that if we just print this assembly after this, we will see what's going on here. 20 lines will be enough. Maybe a little bit more. Okay. Yep. Sorry. Here. Yep. This is just the push, pop, jump that I showed before, just at the end of the function. And afterwards, there is this really weird stuff with even some invalid operations that it really makes no sense for it to be executable. So if you analyze malware, encrypted malware, or something similar, it's like it's screaming, I'm encrypted code, I'm encrypted code. Okay. So, and we have just in the previous function that is just preceding it, that push pop jump with all the previously XORing stuff with moving memory. It's screaming like I'm the decryption of this obfuscated code. So how can we do decrypt it? Actually decrypt it. This is the function that is doing the decryption, and we will basically emulate it. If we emulate that function that is making the decryption of this code, we will see that the code will be decrypted. So okay, let's see if I can do it right. Yeah, here we have the IO cache activated because we will be modifying the code that is just afterwards. It wasn't really necessary in the previous one. I just confused it. The initialization of the machine, we can see the registers, and then this is, we are seek. That seek is just at the very beginning of the function. We seek just before, and we are going to the end of the function, just emulating it. Okay. It will take a couple seconds. That's it. And now, if we print again, 32 lines will be enough. This assembly at that offset, we will see, okay, this looks way better. This looks way better. So we have basically emulated the routine in that function that was decrypting the code that was right below. And as we have emulated it, and we had enabled the cache, it has been modified on memory, but not on disk. RAM memory, but not on disk. So if we exit this file, the file will be just as if it was the very beginning. So that's kind of cool. And it's now, it makes a lot more sense. Okay. So let's go. Yeah, I have some time. So to extensibility and scripting, and I'll go really quick with that. As I previously mentioned, Radare2 is design is composed by several C libraries that are made with no third-party dependencies, and each library can be built on your project or some of them as you prefer. One of the main use case of that and the practical approach is that those standalone programs that I told you before, that Rabin to extract information, Rax for the base converters, the RISM for the assembler and disassembler, are just standalone programs using each one of those libraries, or one or more, two or more of them, depending on the capabilities. And this is the basic structure, like the actual structure when you clone the Radare2 repository. This is the libr folder where you have the modules with dependencies. Then inside each library folder, you have the P folder when you have the plugins, the core plugins for each module. Then we have the B and R for the binary programs, and the shared SHLR, which is code that is read from third party. This is code that is used to perform some of the things. For example, to mount some partitions. It's code that the code that is being used is from the group bootloader, slightly modified, but that's it. I can show you really quickly. Those are the libraries. For example, if we go to the assembly, we have here, and the P is all the assembly plugins. Here you can see the architectures. And those are the programs I told you before. And of course, you have the third-party code that is used in some places. That's it. This is really fancy organizational stuff, and I'm not really sure that it is updated, but it's the most updated version of the graph, at least, of the libraries, the dependency, well, internal dependencies on libraries of Radare2. At the top, we have our util that it's consumed by everything. And then at the final, we have the core, which provides the main API to program. I just wanted to put a fancy picture, but I don't expect you to just now conceive all of that. If you are really interested, just clone it and looking through the code. Just keeping in mind that basic structure is what you need. Plugins for extending. As I said, we have plugins for the assembly and disassembly of different architecture, for file formats, for input, output, and debugging. For example, I won't list them because I don't want to lose 2 minutes more. I will do more interesting stuff with the time. But with those commands there, you just list the plugins that you have. For example, the input-output is cool because you can just connect a session to a socket through somewhere and just work through that. Or they're really fancy input and output plugins to work with. And how to manage plugins that are not in core? Basically via the package manager, R2PM. When we install R2PM, we need to initialize it, first of all, with R2PM init, and then we just install a plugin with R2PM-I, or just R2PM install the plugin. You can check the manual of R2PM. Although all the standalone tools and also R2 has a manual in case you want to see all the options for executing it. But it's quite easy, just installing, and with you uninstall it. And this will provide more plugins that are not in the core of the Radare2, but quite useful, some of them. And scripting, that's really cool. And for some time, Radare was told that it was not really easy to script. It cannot be easier, I'm going to say. And the first thing we have is bindings for many languages, which are automatically generated with Balabind, which is another tool created by Pancake some years ago. So automatically, there are bindings that are being generated for Java, Go, Node.js, Python, and a ton of more languages. And you can use those. But it's not being deprecated, but it's not really being used, those native bindings, and in favor of what is the R2Pipe API, which is the standard and recommended way of scripting on top of Radare2. And it's a standard recommended way because it's really, 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 really easy to use. Basically, you just throw as input R2 commands and you get as output R2 output. That's it. And there is a really cool thing that you remember that I told just a lot of slides before, that if you open that J on some command you receive the JSON output, then there is a special command. You can input R2 commands, and you have one of the, we'll see here in the Python example, install with pip and use import R2 pipe. And these are the 4 commands that we have: only open, cmd, cmdj, and quit. The cmd is just inputting Radare2 commands and receiving the output, and the j is really cool because it performs native JSON deserialization. Okay, that means that if basically in Python, for example, when you receive a JSON output from the sections of the binary you're analyzing, if you have executed a command with the JSON appended and calling with the cmdj, it will return a native Python object, in this case a Python dictionary to work with automatically. So that's kind of cool, and it works for many other languages with the JSON deserialization. Let's see. Yeah. So I'm just going to show you how can we script something interesting that we already seen, just the previous demo of the encrypted code. So let's see how to use R2 pipe to do this automatically and to work with it. And it's not here. This is just the decrypt file. I will show to you. That's it. Import R2 pipe, R2 is equal R2 pipe open the executable, analyze, seek to the function, enable the IO cache, initialize the virtual machine of the SIL, set the instruction pointer to the current seeked offset, and step until the end of the function. That's it. What's really cool, you think, yeah, okay, but what do we do with that? I mean, it's just script that makes something, and what? The cool thing is that with Radare2, we can give an initialization script written in different languages. One of those is Python, and there is also native language, like native syntax. But we can just throw this script as an initialization script to a Radare2 session attached to a binary, which means that when it opens the binary, it will perform those operations, and then you're set. And that's really cool because I will just show to you. I guess it's decrypt. Yeah. So you did the manual stuff before, you put it as a script, and you just pass it as an initialization script. And now when you open it that way, you already have the code deobfuscated to work with. So now we can print it. This is the code that we deobfuscated before. Do you remember this bash pop jump triad and then the code that was obfuscated? So that's pretty cool because we are dealing with some encrypted malware sample or whatever. We can just work, do the manual stuff and decrypt all the things, and then put it as a simple script that does this. And then next time we want to work with that sample, you just initialize with that script, and we have everything decrypted automatically. So that's kind of cool. That's it. Oh, let me show you. I have some time. The thing on Python deserialization. Okay. Indeed, I can do it just right there. Pipe. I'm on a Python shell. Okay, so if I run this, okay, that's it. And now, for example, the cool things. To CMD, print this assembly, 20 lines. That's it. all the colors, everything is converted as well. But what I told you, the sections, for example, the sections example, okay, this is the sections, this is the sections as JSON, but we can consume it as, for example, with CMD now, sections equal, oops. And now we have sections as a variable, which is a list which contains dictionaries. So sections 0 is the dictionary of each section. So we are now, just as simple as that, dealing with native objects in Python. And we can work with that wherever we need. Okay, let's discuss a little bit. I'm running quite out of time, but I guess I will be able to do my last demo on time. So common use cases, I won't go really deep into that because debugging, everyone knows what debugging is, but in case you don't know, it's just stepping through a process, putting breakpoints and seeing what's going on to find bugs or to trace an error, whatever. And the debugging options are under the D of debug command. And for you to be able to debug a program, you need, of course, to open Radare2 in a debug session. This is the -D flag at the very beginning. And there are some interesting things here. The commands work like almost the same as in the emulation. I did it in the inverse way because I was really more interested in show you the emulation part that is way less known than just debugging, but with another interface. But do you remember that with emulation we had the A, E, and then all the commands that were the emulation? Here we have basically the same, but with D. DS to step, DC to continue, DB to set a breakpoint, all that kind of stuff, and you can just read for it here, the question mark, and you have the options, okay? So just a few words about debugging in Radare2. It starts the debugging session not at the entry point as if we were just launching, spawning a shell on a file, but not running, but it starts at the dynamic loader. That's kind of interesting because there is sometimes some cool tricks from malware or other software that are between the dynamic loading and the actual entry point or one of the entry points. And this way we can debug around it before getting to the entry point of the program. Then of course it's a low-level debugger. It's not aiming to replace source code debugging or on your favorite IDE. It's just low-level stuff. What's interesting is that it has the native debugging of Radare2, but it can just debug with many backends. You can use GDB, R2LLVM, which is a backend to use LLVM, which is quite useful if we are debugging any iOS or macOS related stuff. Then, of course, we have R2Frida and some other debugging backends to use. For exploiting, I won't go much deeper, but just pointing some few words that might be useful if you're interested in exploiting stuff. The slash command is for searching the stuff. The first one is just searching for a string. The second is searching for rob gadgets, which I'm sure some of you will be interested, and there are some of them. You can also search for rob gadgets with regular expressions and crazy stuff. It's just, if you just slash and a question mark, you will see all the possible searching modes. But those two are quite useful for exploiting things. Then finding function references, essential with analyze, x cross, exactly. XT for the cross references and the offset of the function. And then we can also find the writable and executable sections of a binary, really simple. Just if we just print the section, it will give us right there. So here we have every section and their permissions. Okay. Then, also we can list the libc imports, which might be interesting if you are doing some kind of libc return to libc, that kind of stuff. It's just IS, see symbols. Okay, we have to analyze it first. No, we have to open something first, of course. IS for those are all the symbols, and we can grab for the important ones. Then, as said, Radare2, as I said before, it can be used for generating the Bruitzen pattern. Those are those patterns that are really used when you are doing some kind of looking for the memory position to inject the shellcode, because they are non-repeating, and when you get the instruction pointer, when you get the crash and you see the value of the instruction pointer, it will be loaded with some of those values, and you can get those values and see, okay, so which offset is actually of my payload to encode your shellcode. It's quite common on exploiting things. And we can, of course, craft the shellcode with Radare2. We set the architecture, the bits, and some code in C. There is also an internal syntax for it, but just tiny C programs, and it will literally give you the shellcode in hexadecimal value of anything you have written. It's quite useful. You can do at the inverse. If you receive the random shellcode on the internet, you can make the inverse process and get what's going on in there. It will give you the disassembly. If you are more interested in exploiting, I hadn't really that much time to make demos on exploiting because it will consume the whole session. But the first two posts are very, very basic, just some more points of what I said here. And the third one is a walkthrough tutorial from my friend Itai, and it's really cool. It goes to bypassing ASLR, the DEP, and all that kind of protections. It's kind of interesting. I will leave the references as well afterwards. Let's move on. For the extras, very quickly, if you are still afraid of the shell interface, you have a graphical user interface. It's the Radare2 official graphical user interface. And I say official because there were like more than 10 graphical user interface for Radar from years, from random people doing GUIs, then not maintaining or not really used by anyone, or even private ones. But this one was initially called Yaito by Hugo Teso, Spanish security researcher. And then some other French guys and other people took the lead of it and rebranded to Qt. And it's evolving quite fast. It has a good team of maintainers and developers that are really active. It's developed in C++ and Qt, and it's released alongside the R2 releases. And if you want to know more, just check qt.re. Debugging is not working yet. You can emulate, but not debug. But it should be done soon, let's say. But it's really cool. That's what it looks like. You have all those panels. You can move things, do fancy stuff with mouse and keyboards and all that stuff. Okay. Then the compilation. I won't go deeper into this, but just for you to know what's going on in the compilation in R2 land. First of all, the compilation is difficult. It's freaking difficult. Just theoretically thinking, the process of the compilation is something hard, really hard. So there are many things that we are doing in Radare2. There is, well, first of all, it's not even mentioned here. If you just throw PDC on a function, you will get a pseudo decompilation. Very, very, very basic. It's very basic. It's not doing like anything, but maybe for a first glimpse, it will be enough, and it's really fast because it's doing very little thing. Then there is R2Deck, which is an ASM to pseudo-C converter written in JavaScript. It's way more advanced than the PDC, but it's not a decompiler as it. I mean, it's not what the theorists would call the compiler with the compiling algorithms and reconstruction stuff. It's just a toy, and a really nice toy, and there is a ton of work behind it, and it works so well, but it's not like a formal decompiler, let's say that way. And you have it available. You can search for it in the GitHub. It's available on R2PM, so in the package manager. Then, as I said, the compiling is hard. So mainly what's being what we have been doing is just calling third party, the compiling stuff. There is another package a plugin to use the Reddeck. Reddeck, I don't know, any of you knows Reddeck? Yeah, cool. It's a decompiler that was open sourced by Avast, the antivirus company. They made it open source, I guess, a couple years ago, or maybe not that much. And there is just the R2 or Reddeck is just a bridge between Radare2 and Reddeck, and it's decompiling through it. Then this is the decompiler project for Radare2, the actual decompiler, with all the decompiler stuff and all the fancy stuff and the crazy stuff, but it has very little developers, and it's mainly developed during the GSOC, which is the Gaggle Summer of Code, or maybe sometimes the RSOC, which is the own kind of summer of code by Radar, not sponsored by Google. But it's work in progress. It's a really nice proof of concept. It can do some stuff, but it's not really ready yet. Okay, but it's in the good direction. It's the one in the good direction. It has some fancy algorithms that are working really, really nice. And if you are interested or want to join it, just, well, you have the GitHub here and open an issue or contact the developers, and it will be really awesome. Then there is one that is not here, but it's possible, and indeed there is a proof of concept done, but it's private and it's not really stable or anything, which is basically using the Ghidra decompiler. The decompiler of Ghidra is quite awesome. For example, Objective-C, it works really well. And there is a plugin, a work in progress plugin, but I would say a proof of concept right now, just using that decompiler as a backend. So that's it. We can throw it any decompiler. Then I guess I have 10 minutes. We'll have enough time. Okay. I will talk just a little bit about R2Frida, which is a really cool plugin. Any of you knows Frida here? Frida? Yeah, I see a lot of faces. Okay. So the ones of you who know, you know that it is amazing. And the ones who don't, is just binary instrumentation on asteroids, many asteroids, and it's freakingly amazing what it can do. But basically, dynamic analysis with binary instrumentation, injecting code, monitoring, tracing, it's amazing. So R2Frida is basically front end for Frida within Radare, and we can do some cool stuff. We have to install it through the package manager, and okay. If we open a R2 shell with the backslash, we append the we prefix with the backslash will be the comments from R2Frida when we have installed it, and we can, oops, no, yeah, because we are not attached to any session. Yeah, I will show you now. So to open a Frida, to spawn a Frida session, we just R2 and Frida. This is the hack to open a process, an actual process, by name of the process, by process ID, or even other stuff, local, remote, anything. And that's it. Those are links to R2Frida, the actual tool, and the unofficial wiki, which is being developed by Eduardo Novella, a friend of mine, which is really cool. And I will show you a very quick demo of what can R2Frida do. And that will be it. Here I have a counter.c that is this stupid code that just prints a number, hacking the box Amsterdam 2019, sleeps 1 second, and increments that number, and it keeps printing. Okay, so let's exit the Okay. That's it. Okay. Now we can open directly just saying the process name. You can look for that process name, but wait. It's here. Trust me, that is the first of the counter. But anyway, you can open also with the process ID. And let's just open it. Yes, I'm open. Okay, now I have, those are all the options with Frida. And I will show you just to show the capabilities of it, very, very basic. Cheat sheet here. I will list information. And I'm interested now in the entry point. So let's see where is the entry point of this process. The process is running. I mean, we are injecting a running process. Okay, keep that in mind. So here we have the entry point. Let's see here. And let's just disassemble. Wait a second. So you can see it better. Okay. And here we have that good thing. So just without understanding anything, we have move AX to 0, then a call, then moving a 1, then another call, and then an addition, and then a jump back to here. So basically, this is initializing the first variable, then the sleep, and this is incrementing that variable. Okay. So as I told you before, okay, with visual mode in this assembly, we have one mode, the cursor mode, which is activated with the C of cursor, and we can just put it in 1 byte. And for example, if we go to here, this one is the one that represents the incrementing value. So if I don't fuck it, it will work. So let's see the counter now. The code is being injected in memory. So I can just more of that. Then let's say it 1. And this one, I told you it was the sleeping time. So if I just increase it, seems it crashed, but it's just that it goes slower. And of course, if I put it to 0, when it finishes. So that's basically it. Very, very basic, but just for you to see what is possible and all your ideas can be freely satisfied. So I have very little time, but I'm almost done with it. I would just want to point you to some documentation and more resources. The first one is it's already documented in C. So yeah, I mean, it's the best way if you want to understand everything, but it's probably not the most practical way to go to it, at least at the very beginning. There is the Radare2 official book, which is continuously being developed. It's in Git books, and then I would call for the we are in the Google Summer of Google Season of Documentation, which is some kind of Google Summer of Code but for documents. So if any of you is interested and is a good technical writer and wants to join us to make the R2 book even better, so you're welcome to contribute to make your proposal. We have also some physical books. I have not any unit with me right now, but we did some physical books really fancy for the past R2 Congress that of course now are outdated, but they were really cool. Yeah, that's it. Then more resources. There is that book, which is a little bit outdated, but still it has a ton of good information. Radare2 exploration. Then you can search for blogs everywhere. Those are just to mention the Radare2, which is the official blog. It's updated very not really often, but it has some articles interesting. And then just to mention one on the internet, I mentioned the one from Megabits because he's my friend. So but it's from him, and he has amazing tutorials and walkthroughs on Radare2. Then, if you want more resources, we have recorded talks. We have all the talks recorded for the 3 editions of R2Con. The first ones are quite low quality because it was a little bit, well, I would say improvised, everything. But the material is really good. And then for the past year and the 2017, those are talks with really good quality, and a lot of content is being covered. And then there are just tons of talks of Radare2. Just check on YouTube about your favorite video search engine. There are tons of talks. But if you just go through all the playlist of Radare2Con, you have a lot of material to see. And some extra tips. Those are really quick before leaving. Is just, okay, remember to pen a question mark. It's just, my advice for everyone is just pen a question mark, and you will be fine. But if you can use a native hat. I have not explained because it was not the case. It was not really relevant. But this 3 points is basically native hat of Radare2, and we just use that. We are gripping on native hat, on the question mark, on all the sub help, the command, the help of all commands and sub commands. And this is basically this very quickly. So here, basically, we can stop this. This is a search like that on all the help. And just make an alias R2help. This is just for do a quiet init and just run this command and not opening any file. That's it. So now basically, I think I already have my R2help, and yeah, that's it. Show, I don't know, hex, whatever. It's a cool tip to have. And for support, there is the IRC, the Radar channel Freenode, and the Telegram channel, and both are bridged together with a bot. So if you talk from one or the other, everyone will receive it. And that's basically it. The conclusions I would say is, first of all, Radar2 is not that difficult, and I hope that got a little bit clear, at least. You have to keep in mind that we are using mnemonic commands that could be different from other mainstream things, but they are not difficult. They are just different. It's a Unix-like shell, so if you are really used to Unix programs and Unix-like interface, it's really familiar. And with less than 10 commands, I haven't used more than 10 commands. We can do a lot of stuff. Yes, we can add modifiers and more fancy stuff, but for the basic stuff and many of the things we will run every day with 8, 9, 10 commands, we have enough. And of course, inline help pending a question mark. Then our conclusions is that there are many ways to contribute to open source projects like Radare2. One is with code, of course, but also writing documentation, using it and reporting the issues. If no one reports the issues that they found, they are not solved. So if you find an issue, just report it. Probably Pancake solves it in 1 minute, but that's another point. And use it and share it with your friends or on conferences, and that's it. And as a final, just 30-second spam, we have the R2Con for 2019. This year, it's community-driven and community-focused from 4 to 7 of September, Barcelona. We have trainings, both basic tracks, so if you are really interested in it but you don't really have an idea, we have 2 days of full basic trainings, 8 hours of Radare2 and then Qt and I guess another one of R2 internals, and then we have another track of advanced ones with code deobfuscation techniques, with symbolic execution, and another with R2 freedom. And then 2 days more of conference talks, technical talks for everyone. And that's it. If you're interested, just check the Congress page, and tickets are online. And that's end of my spam and end of my talk. Thank you very much.
Thank you as well, Arnau.